I will derive the rate law for the sequential first order reactions. This is a two-step reaction. So from A to I, that's the first step. From I to P, that's the second step. We assume both are first order reactions with a rate constant. In the case of A, over here there's a rate constant case of I. So if we see three different species in this chemical reaction, we can write out three differential equations. So first, we'll write the differential equation for A. So A is consumed in the first step. Therefore, there's a negative sign here. And then we're going to look at P. P is produced in the second step, and it's positive. And finally, we'll look at this I, the intermediate. I is produced in the first step. So we'll put a positive sign here. Again, the reaction rate of the first step is Ka times A to the power 1, assuming this is a first order reaction. And over here, I is consumed. So we got three differential equations. And we will have to solve this one first. And this is easy to do. I'm going to just give you the expression for this one. A at any given time t is just A naught times e to the power of negative k a t, because this is a simple first order reaction mechanism. Alright? And then we cannot solve this one because it contains three variables, p, t, and I. How about this one? This one also contains three variables, I, A, and T. However, we know the expression of A. Okay, it's right here. So it's a case of A times the initial concentration of A times the exponential function here. And then minus Ki. Now we have only two variables, I here and here, and T. Unfortunately, there's no easy way to separate the two variables. And if you are experienced with differential equations, you will realize that this I must contain this exponential function and another exponential function. I'm going to show you both exponential function here. So I must contain this, and I must contain a exponential function like this. All we need to do is to determine the coefficients here and here. And I'm going to just use two Greek letters, beta and kappa here. And we will plug in this into here. We will plug in this into here. Okay? I will have to get a bit more space. So I'll go here. I'm going to plug this expression in here. We're taking the first derivative of I, and you can tell it's an exponential function. It's going to be just negative beta Ka, negative Ka times beta, e to the power of negative Kat. We take the first derivative of this guy, which is minus kappa Ki, e to the power of negative Kit. Okay, that's this part. And then we're going to plug in this in here. That's absolutely fairly easy to do. It's just this guy plus this guy, and they have a common factor e to the power of negative K8T. So I'm going to combine this and this. K8 times A naught and beta can be combined. I'm sorry that I forgot to multiply this I by negative Ki, so I need to do this properly. Again, you have K times A naught, and then you have minus Ki times beta times this exponential function. So minus Ki times beta times this exponential function. Alright, and then you have minus Ki times kappa times e to the power of negative Kit. So I'm going to have a negative sign here. And Ki times kappa times e to the power of Kit. Right, I have to erase this part. We just compare this exponential function with this exponential function, and we're going to compare this exponential function with this exponential function. Okay? And you can tell this term, kappa times Ki, kappa times Ki, they cancel. And then we have this guy equals this guy, so it's just negative beta Ka is equal to Ka A naught minus Ki beta. And this way we will determine the expression for beta. Beta is just Ki minus Ka at the bottom, and on top it's Ka. Got the expression for beta. And then we have this I equals beta times e to the power of negative K8T plus kappa Kit, and now we know the expression of beta. We have to know the expression of kappa as well. At time 0, I is 0. Initially, there's no intermediate in the reaction system. This equals beta times e to the power of 0 plus kappa times e to the power of 0. So, by looking at this, we know beta equals negative kappa, and vice versa, kappa is negative beta. And because of this, we can simplify the expression of I. Kappa is negative beta. Why don't we just combine these two exponential functions? That will give you the expression for I. What about the expression for P? The expression for P is very simple if you realize this. A plus I plus P is always equal to the initial concentration of A. Basically, it means if A is consumed, it will become either I or eventually P. And the mass or the chemical composition must be conserved. So we have this neat equation here. And we have the equation for A. A is just A naught times e to the power of negative Kt. We have the expression for I. I is really complicated. because of this beta term, this is Ka over Ki minus Ka, and then you have A naught on top, and then it's the difference between two exponential functions. Plug in the expression of I here, and then you will find the expression of the concentration of the product and how that changes with time.